Welcome to today's lecture. In today's lecture, we are going to see Unit 3. We'll see what are all the contents which are going to discuss in Unit 3. Basically, this is divided into two parts. First part is going to deal only with what are all the random processes which we are going to discuss in noise. The second part is discussing completely about what are all the different types of noise available and how we can characterize the noise in our transmitter as well as in receiver section. And today we are going to concentrate mostly on our first part, that is what is random variable, what is random process, and what are all the type of random processes available. Basically, we'll concentrate more on stationary and non-stationary process and ergodic process, and we'll stop our topic on Gaussian process. Today we'll see Unit 3 random process. What is the definition of random variable? Before going to see what is random process and why we need random process, random variable, this analysis, and what made us to discuss about random process here. We know that our information is an signal. Signal can be divided into deterministic. The second category is non-deterministic. Non-deterministic signal can also be named as stochastic or random. That is, so far we have generalized our expression, a message signal or carrier signal. We have generalized our signal as AC cos 2 pi fct plus phi. So this is our generalized expression for C of t. C of t is our carrier signal. So far we have taken amplitude of carrier term is known, frequency of carrier signal is known, and phase difference of carrier signal is also known values. So therefore so far we have generalized using only the known values. If suppose we don't have any known values, that is future value cannot be predicted. If suppose in our signal the future values cannot be predicted, in that case the signal is referred as non-deterministic or stochastic or random signal. What are all the signals which are coming under this category? Some examples are information signal, or we can name it as a message signal, any audio signal or speech signal or music signal, and interference signal, the second signal which is going to interfere in our path when we were transmitting from transmitter to receiver, that during the transmission or in channel. And the second is noise. Noise may be an internal noise or external noise. What are all the types of noise available and how we are going to characterize noise? Exclusively we are going to study this noise part in part 2 of Unit 3. And how we can analyze these type of signals, the signals which we cannot certainly tell what is an amplitude, what is the frequency, and what is the phase difference, and there are certain signals in which the future values cannot be predicted. And how we can analyze these types of signal? These type of signals can analyze only by using statistical parameters. Can be analyzed by using statistical or average parameters. What are the statistical parameters we have studied in probability and random theory? Mean, variance, autocorrelation, which we are going to study in detail. So the branch of mathematics which deals with statistical and average parameters of random signal is referred as the branch of mathematics which deals with statistical characterization. Statistical characterization of random signal is referred as probability theory. Before going to see what is random variable and random process, we'll just have a glimpse on probability theory. We have studied all this in our 12th standard syllabus. We'll just have a glimpse on what is it. What is an experiment? Tossing a coin, or choosing a card from a deck of cards, or throwing a dice. So what is an experiment? Experiment is a rule for operation. How we have to perform and what are all the sample spaces available, and what is an outcome? Outcome of an experiment, which we refer it as a result. Then what is an event? Combination of result is referred as an event. Combinations of event. So this we already know. And what are all the axioms? Generally we follow in probability. Probability of sample space is certain, that is 1 for certain events, and always the probability value was lying between 0 and 1. Probability of mutually exclusive event is, that is A intersection B is always equal to 0 if A and B are mutually exclusive. And what is another important axiom? What is P of A union B? P of A, probability of A, probability of B minus P of A intersection B. And what is our fifth axiom? We know that Bayes theorem, that is based on conditional probability. What is Bayes theorem? Probability of A by B is equal to probability of A, probability of B based on A divided by probability of B. So this is a conditional probability theorem. These are all the references for the topics which we are going to discuss further. The next is, we are going to see a random variable. Initially we have discussed about what are the types of signals available, and we discussed about what is probability theory. Now we are going to throw light on random variable. What is random variable? Mapping of an outcome of a random experiment to a real number. It is referred as a random variable. Mapping of an outcome. Outcome is result of an experiment. Therefore, mapping of outcome of an random experiment to a real number. Then it is referred as random variable. For example, assume we have domain of X lambda 1, lambda 2 up to lambda I, lambda k. So this is our set of all outcomes. These outcomes are result from domain X. So this is an experiment. So these are the set of outcomes derived from the experiment X, and this is our real number. Possible output values, range of what are all the values this outcome can obtain, range of X of k. So this is 10, 20, somewhere around 100. So if we map lambda 1 to 10, lambda 2 to 20, lambda k to 100, this mapping is referred as random variable. X of lambda 1, x2 of lambda 2, xk of lambda k. This is the description of random variable. If I have finite discrete values, my random variable will be finite. Discrete values, then my random variable is also discrete. If I have continuous value, then my random variable also continuous. And then what is, for example, assume we have a resistor. Assume this is resistor R. So what will happen if we connect an ammeter to this resistor? So if I connect a battery, I will get a DC signal. When a current passing through this resistor, I will get some DC signal to measure the current and voltage. What happens when I connect ammeter directly across a resistor? See, I will get a waveform like this. That is, due to the Brownian motion, the passing of free electron we can measure and waveform like this. Then non-stationary signal, that is non-deterministic or stochastic random signal. So, this I have asked student 1 to perform this experiment. So, similarly we will give some n number of resistors to n number of students. So, he will get different waveforms, everyone will get different waveforms. Sn. So, if I take this time instant, this is time instant t1, this possible values lambda 1, lambda 2, lambda 3, this value is called the range. When I map this value, then it is referred as an random variable. I can also name it as sample values. The most important property in random signal is probability density function at t1. If I take another signal at t2, another time instant, I have taken another time instant, the probability density function at a t2 will always be equal to probability density function at a t1. That is why we are exploiting this property of statistical property of random signal for analyzing the nature of interference signal, for analyzing the nature of noise signal, because these interference and noise signals are going to accumulate on top of our information signal while propagating the information from transmitter to the receiver. So, we have to study in detail about what is the characteristics of an interference signal, what is the characteristics of noise signal in order to design our receiver. In order to nullify the effect of interference and noise signal, the characteristic study and detailed analysis of this random signal is necessary. Now, we are going to see the second parameter, random process. Just now we have seen random variable. What is random process? Random process is a function of two variables. Fn in short we refer as function. It is a function of two variables. What are all the two variables? One is an lambda, that is outcome, and another one is time, t, and outcome lambda. Therefore, I can refer this random process as a function of lambda t comma lambda. And how to model this parameter? That is how to model this random process. Lambda 1, lambda 2 up to lambda k. We map this to a complete waveform. See, earlier in random variable we have taken only the particular instant. When we take the whole experiment, then it is referred as a random process. In this example, we have taken a different types of signal. Earlier, we have taken a random signal from a resistors, from a different resistors. Now, each student is performing an experiment and they are having different type of signal. One student is having a sinusoidal signal, another student is having an waveform like triangle, and some student is having a square waveform. Therefore, if I map an outcome with this, and if I map an outcome with the second waveform, and the lambda k is mapped with S and k. Therefore, x of t comma lambda 1, x of t comma lambda 2, and this is the signal is referred as x of t comma lambda k. So, this is a set of all waveforms. This collective process is referred as random process. This is our outcomes. In digital nature, for example, I will have an assume a square signal. I will have D1, I will have pattern of 1, again 1, 0 and 1. What is it? 1, 0, 1. I am having signal called 1, 1, 0, 1. In the second digital pattern is 0, 1, 0, 1. The second pattern is 0, 1, 0, 1. So, at time instant T1, at time instant T2, at time instant T3, T4. So, this if I take this, then it is referred as random variable. When I take collective sample, then it is referred as random process. These are all referred as time instance. How many options are possible here? Since I have taken 4 bits, 2 power 4, 16 combinations are possible. This characterization of a random process, it depends on joint dependency. In random variable, and it is depend on probability density function. Here it is depending on the joint PDF, probability density function, in order to analyze 2 random variables. If for example this is D1 and D2, then I have to analyze what is the pattern for the second, or what is the prediction of output for the second at time instant T2. Then I have to analyze joint probability density function between these two, T1 and T2. And the next important parameter which we are going to discuss is cumulative distributive function. Cumulative distributive function. In short, we refer it as CDF. Cumulative distribution function. We are going to see what is the definition and what is the formula for cumulative distribution function. What is CDF? CDF is usually represented in terms of f capital X of small x, and it is equal to probability of, that is set of x less than or equal to x. So this is the formula for cumulative distribution function. Fx of x is, or in some books it is referred as f of x alone. For example, refer the waveform here, the staircase type of waveform. It's a cumulative addition. See, here it's 0, 0.5, sorry 1. It goes on increasing 0.5. This value is 1. This is my cumulative distribution function. And here it is x. This type of waveform is referred as staircase. What is the value for x less than 0? My value of f of x is 0. Then what is the value of x equal to, less than or equal to, sorry, greater than or equal to 0 or greater than or equal to 1? My value is 0.5. F of x is equal to 0.5. What is the value of, sorry, less than or equal to, right? Less than or equal to. What is the value of x greater than or equal to 1? My f of x value is equal to 1. So it is always an increasing function. It will be helpful for analyzing the properties of cumulative distribution function. What are all the properties? Properties are, we know that probability of the function is always greater than or equal to 1, that is 0, bound between 0 and 1. Therefore, cumulative distribution function minimum value and maximum value is between 0 and 1. F of minus infinity is equal to 0 and f of plus infinity is equal to 1. The third property is, since it is an increasing function, probability of a less than or equal to x less than or equal to b is always p of b minus of p of f of a. And what is the fourth one? It's a non-decreasing function. It cumulative addition, therefore it is always be an increasing function. It's a non-decreasing function. Based on the cumulative distribution function, random variable is characterized. For example, when I have a discrete CDF, my random variable is also discrete. So this is x with respect to f of x. When I have a continuous variable, this is my f and this is my f of x, then my random variable is also discrete in nature. When I have continuous variable, continuous distribution function, my random variables also be continuous. Therefore, the characterization of based on the CDF, random variable can be characterized. Therefore, when I have a mixed nature, what will happen? In that case, when I have a mixed CDF, the random variable is also will be in the nature of mixed. The next parameter which we are going to discuss is probability density function, PDF. Probability density function, which is the most important property for analyzing the autocorrelation as well. And then what is PDF and how it is derived? It is derived from the PDF. It is referred as f small f of x. It is the derivative of cumulative distribution function. Therefore, derivative of cumulative distribution function. So, this is the formula for probability density function, and this is for cumulative distribution function. And what are all the properties? Since we have studied everything, that is what is cumulative distribution function, probability density function in probability and random theory, we are going to discuss only the formulas and properties. And what is the property of for probability density function? The property one is fx of x is greater than or equal to 0. The second one is integral over minus infinity to x fx of x dx is equal to 1. That is area under, what it means is area under probability density function is unity, and integral over minus infinity to x fx of infinity alpha, fx of alpha into d alpha is equal to fx of x. And what is the fourth property? P of x1 less than or equal to x less than or equal to x2, integral over x1 to x2 fx of x into dx. So, these are all the 4 important properties of probability density function. Next, we are going to see what is mean, variance and covariance. What is mean? It is defined in mu x of t. The formula for me represented as mu x of t is equal to expectation of x. This parameter is referred as expectation. Expectation of random variable x. It can also be mentioned as minus infinity to infinity fx of x into dx. This mean is referred as an first order probability density function. Therefore, mu x of t is equal to minus infinity to infinity x of fx of x into dx, or it can simply be referred as expectation of x. The second parameter is variance. Variance sigma square, and it is mean square minus square of mean. The formula is expectation of mean square minus square of mean. And what is in covariance? Covariance is Cx of t1 comma t2 is equal to expectation of x of t1 minus mu x into x of t2 minus mu x. That is a two sample instance, the same random variable at time instant 1 and the same random variable at time instant t2. This, when you analyze this, then it is referred as a covariance. What is autocorrelation? Autocorrelation is referred as Rx of t1 comma t2, expectation of x of t1 x of t2. It is referred as double integral, therefore minus infinity to infinity x1 x2 fx of t1 into x of t2 x1 comma x2 dx1 dx2. So, this is referred as a second order probability density function. Mean is your first order probability density function, autocorrelation is your second order density function. Predominantly these two parameters, mean and autocorrelation, is we are going to discuss in further processes. And then what are all the properties of autocorrelation? Rx of tau can also be referred as expectation of x of t plus tau x of t for all values of t. First one is Rx of 0, expectation of x square of t. When you substitute 0 here, x of t into x of t, therefore x square of t, then it can be referred as average power. When you have the tau is the time difference, when you have that 0, then the resultant autocorrelation is nothing but the average power of the sample value. Then what is Rx of tau, which is equal to Rx of minus tau. odd and even property by exploiting the odd and even property. Rx of tau is always less than or equal to Rx of 0. The proof is, we'll see the proof later, and it is a deterministic. Autocorrelation function is deterministic in nature. This is also important. Okay. Next we are going to see, these are all the important parameters for discussing the random processes. Next we are going to see stationarity. What is stationary process? Stationary, statistically independent of time. Statistically independent of time. When we have an process, if that is independent of time, then it is referred as stationary process. When it is statistically dependent on time, that is at every time instant called t1, t2, that is it depends on time, then it is referred as non-stationary process. It is basically characterized as strict sense, stationary. In short, it is referred as SSS process. The second category is wide sense, stationary. WSS. And we'll see what is SSS, that is strict sense stationary process. Okay, the definition for strict sense stationary process is given by, let x of t is initiated at t is equal to infinity, let x of t is initiated at t is equal to minus infinity, then x of t1 and x of t2 and x of tk denote the random variables. The joint distribution function is given by f of x of t1 comma x of tk x1 comma x2 comma up to xk. This denotes the joint distribution function. Joint distribution function. So this is x of t1 comma tk are referred as random variable. If we shift all the observations to a fixed amount tau, that is we have taken this random variable. If we shift all the random variable that is if we shift all our observations, this random variable is nothing but an observations. If we shift all the observations to a fixed time called tau, then what will happen? The resultant will be x of t1 plus tau, x of t2 plus tau, then x of tk plus tau. The joint distribution function for this is given by f of x of t1 plus tau, xk of x of tk plus tau, x1 xk. So this is our joint distribution function. The random process x of t, this is a joint distribution function. So when we state our process is a strict sense stationary process, the random process x of t, this random process x of t is said to be stationary in strict sense or strictly stationary if the following condition holds. What is the condition? If x of, when we shift all the observations to a time instant called tau, x of tk plus tau, x1 comma x2 comma up to xk, f of x of t1 up to tk, x1 comma up to xk. So for all values of tau and for all values of k and for all values of t1 to tk. If this condition holds, that is even after the fixed amount of time shift, when my joint distribution function before and joint distribution function after the time shift, when this two joint distribution function holds equality, then my resultant signal is referred as, resultant process of x of t is referred as, this x of t is my random process. This is my random variable at each time instant. Then my random process is referred as strictly stationary or strict sense stationary random process. The two important properties of random process which we are going to study are properties. Just now we have seen at what condition the property holds true, that is fx of t1 plus tau up to x of tk plus tau x1 x2 up to xk, which will be equal to fx of t1 comma t2 up to tk x1 x2 up to xk. So this is for all values of t, for all values of tau and for all values of k. T means from t1 to tk, from the time instant starting from 1 to k. What will happen when I have k is equal to 1 in this equation? For example, consider this as equation number 1. What will happen when k is equal to 1? I will have only the one instant, fx of t1, 1, obviously first one, fx into x, which will be equal to, here also, f of x of t plus tau into x. So what this denotes? Fx of t plus tau of f is equal to fx of x, which denotes the cumulative distribution function for all values of t and for all values of tau. This is the first order distribution function of a stationary random process. Independent of, here we have seen, which is independent of time, which is independent of time. What will happen when I have k is equal to 2 and tau is equal to minus of t1? Here fx of t1 comma t2 into x of 1 comma x2, which will be equal to x of t1 value. What is my t1 value? t1 plus tau, therefore t1 minus of t1, which will be equal to 0 comma x of tk. What is my tk? K value is equal to 2, therefore t2 plus tau, therefore minus of t1, therefore t2 minus t1 x1 comma x2 for all values of t1 and t2. Then what will happen? What this infers? This infers the second order distribution of function of a stationary random process. It depends only on the what it states. T2 minus T1 is referred as the time difference tau. Time difference tau. Therefore, it depends only on the time difference tau, not on, depends only on time difference tau, not on the individual times, not on individual time instance. What are all the individual time instance? T1 and T2. So this two property, when this two conditions k is equal to 1 for first order distribution and k is equal to 2 for second order distribution, when this two condition holds good, then we refer that type of random process as strictly stationary or fixed sense stationary process. Then what is wide sense? WSS. Wide sense stationary process. Analyzing k is equal to 1 and k is equal to 2 up to k is equal to some random number, for each and every process will be tedious and it will result into an number of expressions, and it will be time taking also. And what we infer from this, for White's and stationary process, we analyze the two important parameters called mean and autocorrelation, because mean is our first order stationary process and autocorrelation is second order function. Therefore, we are utilizing that parameters for analyzing the White's and stationary process. A process is said to be WSS if my mean of a strict mean of SSS strict and stationary process is constant. So we don't have to go and extend further for k is equal to 3 and k is equal to 4 for n number of orders. If we find out that our mean of SSS process, SSS process is constant, then we infer that condition 1 for White's and stationary process is true, that is independent of time. Constant means it is for all values of t, then it is independent of time. And what is autocorrelation? This is our second order probability density function, autocorrelation. For example, what is the formula for autocorrelation? T1 comma T2. If this autocorrelation depends upon of T1 minus of T2 minus of T1. What is T2 minus of T1? Rx of tau for all values of T1 and T2. That is expectation of x of t plus tau and x of t. When tau is equal to 0, Rx of 0 is equal to expectation of x of t square. So, when this condition holds good, then our WSS process is referred as second order. If this condition holds good, then it is referred as first order weakly stationary process or White's and stationary process. And if this condition, autocorrelation condition for is also true, then it is referred as second order stationary or weakly stationary process. Next, we are going to see ergodic process. Before going to see what is ergodic process, we will see what is ensemble average and what is time average. So far in a strict and stationary process or in White's and stationary process, we have studied only the ensemble average. What is ensemble average and what is time average? We have to study in detail. What is ensemble average means? When you study a process or when you take the samples across, for example, if here you have an waveform like this. This is your waveform number 1. Here you have an waveform number 2. This is for waveform number 2, and similarly you have an waveform n. See, assume this is our times instant t1 and this is our time instant t2 up to time instant tk. Ensemble average is when you take an average or instance across the waveforms, then it is referred as ensemble average. That is across the process. When you take a sample values along the process, then it is referred as time average. Then it is referred as time average. When this ensemble average across the process and time average along the process, when these two averages are equal, then you refer that type of process as an ergodic process. What is ergodic process then? This ensemble average, this is referred as mu x of t, ensemble average is referred as mu x. When our mu x of t and time average is equal to ensemble average mu x, then that type of process is referred as an ergodic process. Mu x of t is our time average, mu fx is our ensemble average. When these two are equal, then we refer that type of process as an ergodic process. For example, in ergodic process, we know that what is mu x of t? Mu x of t is equal to 1 by 2t integral over minus t to t x of t dt. That is 1 by 2t integral over minus t to t expectation of x of t dt, which will be written as minus infinity to minus t to t mu x of dt, which can be taken as 1 by 2t mu x of t of minus t plus t, which will be mu of x. Therefore, time average, which is equal to ensemble average. What is the classification of random processes? So, insects in stationary, whites in stationary. On top of it, we can say ergodic, or sorry, on top of it, we can say random processes. So, this is the classification of random process. That is all. Here ergodic will come in this picture. That is, if I have a Whiteson stationary process, then it is Sticksense as well as ergodic. When I have a triple S process, it may be ergodic but need not be a WSS process. So, this classification is necessary for the understanding of what is ergodic and how this hierarchy goes. All the ergodic process are triple S, WSS, but all the WSS process, all the SSS process need not be WSS. And the second next property is power spectral density. We are defining power spectral density in terms of autocorrelation. This is by using the Wiener-Kirchner theorem. Wiener-Kirchner theorem. With the help of Wiener-Kirchner theorem, we are stating as Fourier transform of autocorrelation function is nothing but an power spectral density. Therefore, Sx of f is equal to integral over minus infinity to infinity Rx of tau e power minus j 2 pi f tau d tau. This is the Fourier transform function. Therefore, Rx of tau inverse transform is given by minus infinity to infinity Sx of f e power j 2 pi f tau into d tau. So, this is the important theorem in power spectral density. And the last process which we are going to see is Gaussian process. What is Gaussian? So, if I have a random process, when random process is said to be Gaussian, all the random variables are jointly Gaussian. For all values of k and for all values of t, then it is referred as a Gaussian process. Or I can state it as, if every linear function of x of t is a Gaussian random variable, that is, if every linear function x of t, linear function of x of t is a Gaussian random variable, then that type of process is referred as Gaussian process. What are the properties? If I input to the system is Gaussian, then the input to the linear time invariant system. If input is Gaussian, obviously the output is also Gaussian. The second property is, if two random processes are jointly Gaussian and uncorrelated, if two random processes x of t and y of t are Gaussian and uncorrelated, then they are said to be statistically independent. And the third property is, it can be completely described by its mean and its autocorrelation. With the help of mean and autocorrelation, it can be completely described. What is the fourth property? Gaussian process is WSS. If and Gaussian is WSS, then it is strictly stationary too. So these are all based on this Gaussian process. When my mean is equal to 1, mean is equal to 0, and variance is equal to 1, then that is referred as a central limit theorem. Gaussian process, for a Gaussian process, if I have a mean is equal to 0 and variance is equal to 1, then with the help of central limit theorem, then it is referred as a Gaussian process. And what is a white noise? White process, for the power spectral density is constant, that is, it is always equal to n0 by 2 power spectral density, then it is referred as white noise process or white process. So far we have seen stationary process. In stationary process we have seen triple S and WSS, and ergodic process. The next process which we have discussed is Gaussian, and the last one is Weisstein's stationary process.